Okay. So hello everyone. This is day 5 now. I wasn't able to stream for a long time because I got caught up in computer networks and other subjects. So I'm finally here again, and let's begin. Today my goal is to just study this Ramses theorem and last question, 15th question, then start the first chapter. Okay, so let's begin. Ramses theorem. To understand it, I might use some AI. What is this? Ramses theorem. So, the core idea is really about binary choices and pigeonhole principle. Okay, what's on the plate? First, what is the theorem saying? You have graph G with n vertices. For any collection of vertices, there are two extreme possibilities. Okay, fine. First extreme possibility is clique. That is, every pair of vertices is connected. Fine. Then a clique of size k is usually written as k with subscript of k. Every single vertex is connected, fine. And anti-clique is an independent set where no vertices is connected. Are you telling me this is this real graph? I mean, won't you say these are four different graphs? Or because we are not connecting any line, wait. I want to search. Is this? My caps lock key. Just give me a minute. I don't know why this. I need to restart. Okay. Finite RAM says okay. What was my question? Okay. If there are no connected vertices in a graph, is it still a valid graph? Is still a valid graph. By definition, a graph is simply a set of vertices combined with set of edges. If the edge set is empty, the structure remains a completely valid graph containing isolated vertices. Okay, unless it has zero or one vertex. Uh, no path. What do you mean by this? Unless it has zero or one vertex. Acha. Trivial rules apply. No path exists between any pair of distinct nodes. Or let's say there are many vertices, but the way maybe I'm phrasing wrong, but I think it will understand. Let's say there are many vertices, but the way they are connected in such is such that it looks like different graph entities. Can we still say it all as one single graph? Yes, that is still considered as one single graph. In graph theory, a graph does not need to be physically or visually connected to be treated as a single mathematical object. Understanding disconnected graphs. Okay. So okay, that is a doubt I cleared because I think in second stream, the second or third stream, no, third or fourth actually, in previous two streams, there was a point where I made a connection between set theory and graph theory, and I actually made a kind of graph which looked disconnected totally, and a friend of mine commented on that fact, that they think it is uh, it is different graphs basically, but okay, I think it can all be called now one single graph. So coming to the flow. Okay, so anti-click graph is basically an independent set. These four vertices and zero edges between them. Fine. The theorem says every graph with n vertices contains either a clique or an independent set having at least this much vertices. And this number is quite surprising because this, how can a number pop up out of nowhere? This is so beautiful. Uh, it says that no matter how cleverly you construct the edges, you cannot avoid having a reasonably large group of vertices that are either all mutually connected or mutually disconnected. Let's understand why this should be true. Imagine you pick one vertex V. It has n minus one vertices, other vertices around it. Okay, I will, and isn't this a group? Uh, Sorry, switch it. Yeah, is it now a group? Yes. So it is basically saying me, what's the key? Okay, is it still a group? Fine. It is saying me that let me draw first n vertices. Okay, why can't I switch? So annoying. Huh? What? I'm clicking with it. So weird. Windows. I hate Windows. Let me draw n vertices. Let's just draw five of them. Okay. So annoying. It has n minus one vertices around it. Now every other vertex is in exactly one of the two categories. It is connected to V or it is not connected to V. Fine. So n minus one vertices are split into two groups: neighbors of V and non-neighbors of V. Okay. Okay. Fine. And by pigeonhole principle, one of these two groups must contain at least half of the vertices. Okay, this line is something I need to understand. Let's call the group. So annoying. Do I have to wait? Okay, now it works, but I want to make it like this. Okay. Okay, somehow it is working now. Let's call this W. I will connect it to some random vertices. Okay. Let's call this as a neighbor, and that is a neighbor, and those two are disconnected. So according to just concept just I saw, this is still a valid graph. Fine. Let's apply the theorem on. Wait, is it still not working? Oh, okay. N minus one vertices are split into two groups: neighbors of V and non-neighbors of V. Should I name these? Let's just say I call this N1. Uh, call this N1, N2, N3, and N4. And here we see for this W, okay, um, N2 and N3 are neighbors, okay, and N1, N4 are not neighbors. Fine. So what? By pigeonhole principle, one of these two groups must contain at least half of the vertices. कम से कम half. Okay. At least half. Half is 2.5. 2.5 can't be possible. So how? No. There is at least half. Okay. Yes, at least half. More than this group contains three vertices, right? Yes. So that rule, at least 2.5 is true. Hmm. Fine. Maximum of these two groups. Okay, you are calling neighbors as fine. This is very intelligent, I would say. Neighbors of W equals something, and to actually count the number, you are taking absolute value, and that is equal to two. Would I say two? Because you know there are two neighbors, and if we count itself, then okay. So one of these two groups must contain. We are talking about whole group and not neighbors. Okay, we're talking about whole group. So this is three, and the complement of this function is actually two. And as we see, total number is five, and this group contains at least 5 by 2. But why are you doing n minus 1? Okay, so the other n minus 1 vertices are split into two groups. Okay, fine. Ah, the groups are actually excluding this. Okay, so what are the groups? See, this one is a group, and let's just highlight with this. This is a group. Okay, and because the rest of the group is basically total n minus 1, if we if we say at least half, we are taking at least half of we're taking at least half of um, rest of the groups. So this is Not 2.5, but 2. 2. At least 2 is true because 3 is greater than 2. And no, because now both of these groups have two elements. So yeah, at least 2, yes. It's clearly understandable now. I don't need that. This is the entire engine behind Ramsey's theorem. And here's where it get clever. Suppose the larger group is the group of vertices connected to V. And how will you transform this number into logarithm? That part will be more interesting. Suppose the larger group is the group of vertices connected to V. Let's call it S. But here there is no larger group. I've actually constructed the vertices such that both groups are equal. So let's take another example where groups are unequal. All right. I will take, let's say, 7 points now. And this is W basically. I will connect it in the two elements yet again. And now I see one group is here and other group here. So now the value of this function will be 2 and this one is 3 connected to V. Okay, just a reverse of this example. Okay, let's call it S. Should I make it? Man, this is so. Let's just read further. Now forget about all other vertices. We only care about S and what happens inside S. There are again two possibilities. Suppose we find another vertex U belongs to S. Okay. The other vertices in S are again divided into vertices connected to U and vertices not connected to U. Again, one of those groups contains at least half. Okay. What is this? We only care about S, what happens inside S. I will connect these three elements fine. This is one group and this is another group. Now, fine. According to larger group is the group of vertices connected to V. I will call this V now. V is basically every vertex in S. Okay. Now forget about all other vertices. We only care about S. What happens inside S is there are again two possibilities. Suppose we find another vertex U, it belongs to S. The other vertices in S are again divided into vertices connected to you and vertices not connected to you. Okay. Let me just point this one out. Let's say this is you. Now again, this whole set that is S. These 4 points I think belong to S. Now in this set of 4 points, I have just one point connected and the rest all are disconnected. Fine. So if I talk with perspective of you inside the confinement of S, I think, if I'm phrasing myself correctly, then n neighbors of you will be non-neighbors, no, neighbors. Yeah. Neighbors of you will be 1 and non-neighbors of you will be 2. Fine. And this is basically in this set of S. What is S? S is basically this group right here. So we can repeat the process. The important part is we are building a homogeneous group. Let's say we keep choosing the connected side. Suppose we start with vertex 1, then choose a large set of vertices connected to V1. From that set, choose V2, such that V2 is connected to remaining candidates. Then choose V3, which is connected to all the remaining candidates, and so on. We get every newly selected vertex is connected to all previously selected vertices. Every new selected vertex is connected to all previously selected vertices. How? Suppose you can choose V1. V1 is connected to V2, V4, and V3. Basically, it is connected to everyone. Fine. Now I chose V2. V2 is connected to V1 and V4. Okay. Now I chose so V2 is connected to all the remaining candidates. Uh, okay. By that logic, all the remaining candidates. By that logic, V1, I have to choose V4. Since that V2 is connected to all the remaining candidates, then it's again, then choose V3 connected to all remaining candidates. Every newly selected vertex is connected to all previously selected vertices, the way we are choosing. Therefore, this becomes a cleave. But what if we repeatedly chose the non-connected side? Suppose V1 is our first vertex. We choose vertices that are not connected to V1. Then we choose V2. Now we choose vertices that are not connected to V2. Then V3. And therefore, we basically say nothing is connected. So at every step, we have a binary choice, connected or not connected. And whichever side we choose, there are roughly half as many candidates left. And that's the key idea. Let's visualize the shrinking. Suppose we have suppose we start with n vertices, and after choosing our first vertex, at least half of the remaining vertices survive. roughly left with this value. Well. This is kind of hard to comprehend for me. How? Why the theorem has. No, that is understandable, okay. You just took logarithm here. But this part right here, this binary connection of halving things. How? Let's see the process on 64 vertices. Start 64, okay? Pick any vertex one, okay? At least half of the remaining vertices are either neighbors or non-neighbors. Okay. Pick V2 again. We'll see half of the vertices connected to this one is either connected or not connected. And that relation goes on. At every step, we have made a binary decision: adjacent, non-adjacent, choose. Okay. If our decisions consistently correspond to adjacent, okay, leave it. The selected vertices form a clique, sorry. If they consistently correspond to non-adjacent, why am I not able to pronounce that? Okay, this is getting funny. Adjacency, adjacent, adjacency, adjacency. Okay. If they consistently correspond to non-adjacency, sorry, okay, they form an independent set. There is even deeper way to see Ramsay's theorem. This theorem is where theorem becomes really. This is where theorem becomes okay. Forget graphs for a moment and take n people at a party. For every pair of people, color of the relationship either red, they know each other, blue, they don't know each other. If there's sufficiently many people, you are guaranteed to find a group where everyone knows everyone else, or a group where nobody knows anyone else. And that is exactly the same mathematical structure. Red edges friendship and blue edges no friendship. A red click means everyone knows everyone. A blue click means nobody knows anyone. And this is the essence of Ramsey's theory. Complete disorder is impossible at sufficiently large scale. Some structure must emerge. One subtle point in your textbook's wording. Your textbook says a clique is in G is a subgraph in which every two nodes are connected by edge. Strictly speaking, when we say clique of G, we usually mean a set of vertices that are pairwise adjacent along with the edges between them. Likewise, an independent set is a set of vertices with no edges between any pair. Okay, this distinction isn't important for the proof, but it is useful in terminology to keep straight. Pick a vertex, at least half of the vertices either connect to it or don't. Keep the larger half and repeat. If you repeatedly chose neighbors, you construct a clique. If you repeatedly chose non-neighbors, you construct an independent set. Such, since the candidate set is halved each time, the process lasts logarithmically many steps. And that is Ramsey's theorem at the level this exercise is talking about, asking about, asking for. Okay. One thing I'd recommend, okay, the famous result R333. much weaker than famous exact Ramsey from number results. For example, the famous result, okay, says, oh, why am I saying okay each time? I'm annoying myself. Every graph with six vertices either contains a triangle or an independent set of three vertices. And five vertices are not enough. Your exercise gives general logarithmic bound. I don't want to prove it by induction. Induction doesn't give you any intuition for the subject. I wanna ask, if I pick second vertex, if I pick for the second or basically the do we if I want a clique, how can I possibly guarantee that the next vertex I pick is connected to everyone I've already picked? You don't guarantee it globally. You deliberately shrink the pool of candidates so that it is guaranteed. Let's do one concrete example from scratch. We have eight vertices. Suppose we have this graph. Now don't worry about exact. Now don't worry about exactly about the exact drawing instead. Let's use explicit edge list so that there is no ambiguity. We have these vertices and we have these edges. Now let's actually execute the Ramsey argument. Pick any vertex. Let's say we picked A. Now look at other vertices. Which ones are connected to A? Let me draw this EFG. Fine. Is it connected to C? Yes. That is it for how these 3 points are again connected to F. Then fine. Yeah. Don't worry about exact drawing, okay? Pick any vertex A. Which ones are not connected? E, F, G, H. There are 7 remaining vertices. Two groups are, okay. The larger group is this. So we throw away B, C, and D. This is the crucial move. Now we are saying I'm going to search for every eventual clique or independent set among E, F, G, H because every vertex in this set has the same relationship with A. That is, none of them is connected to A. Now pick E, but here's where your question becomes important. What if, wait, if we are trying to build a clique, shouldn't E be connected to A? No, we don't know yet whether we are building a clique or an independent set. Remember, E is not connected to A. Therefore, if we eventually choose E, A, E, are already giving us an independent set direction. Then we chose E because E is not connected to A in any way. E is connected to B and F only, not connected to remaining set. Remaining set is except B and F. We have G and H. So E, G and E. Wait, how are they connected to E? Remaining candidates F, G, H. How? F. Oh, those are all remaining candidates. That is fine. Okay. E, F, E, G. You're saying those are connected. It hasn't taken B, D. It says choice. Wait, why are you taking C, G? C and G are no way connected. Just assume. Don't worry about the drawing. That's why it said don't worry about drawing. It's just taking random. Explicit edgeless. Okay, so let me draw this one. Okay, A B A C A D, A B A C A D, B C B E B F, B C B E B F, C D C F C G, C D C F C G, D E D G, D E D G, E F E G, F G F H G H, F G F H G H. Fine. I could move this point, let's say somewhat here. If I rotate, I think that is fine. Okay. We took A, the rest of the edges were these ones. Then we took E, the rest of the edges are these ones. E, F, E, G, but EH doesn't exist. Yeah. Again, we split the candidates, neighbors and non-neighbors. We throw away the larger group is this, so we throw away H. Now our surviving candidates are F and G. And look at what we've accomplished. We have A not connected to E, E not connected to F, E not connected to G. Wait, that means our choices have changed direction. That's okay. Let's pause here. This reveals something extremely important. The algorithm is not to keep picking vertices that are connected to everyone. At every step, the partition the remaining candidates according to their relationship with the newly selected vertex, then keep the larger group. The relationship could be connected and not connected. We don't decide beforehand. That is the entire process. That the entire process must be a clique. The graph itself forces us into one of the two structures. Let's use a cleaner example. Pick A. A has four neighbors, three non-neighbors. Larger group is neighbors group. We picked neighbors group. Select an element from this neighbors group. Let's say B. B is connected to surviving candidates are three more. B not connected to C, D, and E. Then fantastic. All three survive. Now our situation is this, and we know A not connected to B, A not connected to C, D, and E. B not connected to C, D, and E. Ah, fine. Therefore, C, D, E are also mutually connected. But we don't know that yet. Yes. Yes, you're right. Pick C. Is connected to D, but C is not connected to A. We have selected A, B, C. Is a click. Yes. Suppose instead, suppose at some point we have selected and we are specifically following the connected branch every time. That means we have selected B, threw away every candidate that was not selected to be connected to B. Every remaining candidate is connected to A and B. When we selected C, we again throw away every candidate that is not connected to C. Let's just say I pick, let's just say I pick A. Now B, C, D, E, F, G, H. Let's say I chose F now. Okay. For F, this will be within this group, right? Or should I say everyone? If I say everyone, the neighbors of F are basically C, E, C, E, G, H. Neighbors of F, A, B, D. Now let's choose C. Okay. I think I should not include C in this structure, right? I should not include C. If your goal at this point is to continue the independent set branch, then you should not include C. Your calculation is actually showing exactly why. Let's carefully trace your graph because this is much better way to understand the proof. You picked A, okay. You have both have four vertices, so we can choose either side. Bigger set is this one. At this point, we are naturally looking at the possibility of building an independent set containing A and F, and our remaining candidate pool is this. Wait, there is there is an important subtlety here. If you are doing the proof correctly, once you choose F from this set, you don't go back and consider B, C, and D. Why? Because B, C, and D are already excluded from the branch we are following. But your NF calculation is still useful. This is correct. Now we need to intersect these with current candidate set. After choosing A and then F, our candidates are E, G, and H. So this is the candidate set. So we don't care about B, C, and D anymore. You have to take intersection between these, and then you will simply find that C is not going to be included in the set. Fine. E, G, H. Yeah. So in a given graph, every remaining candidate is connected to F. E, yes. F, G, yes. H. Yes. Let us intersect. Okay. Which is the larger one? NF. We have A not connected to F. We have F connected to E, G, and H. And we can't consider B, C, D, right? So this whole set is just gone. So in your graph, every remaining candidate is connected to F. So if we are trying to build an independent set, we are stuck. We have A not connected to F, and then whatever candidates remain, every one of them is connected to F. So we have these two elements, and this is an independent set, but we cannot extend it using the remaining candidates. So where does C fit? I should not include C in second step here, right? Correct. If a current branch is this, then C is already gone because C belongs to N of A, and while you choose this set, you made a choice between two groups. I chose this one. Therefore, these candidates are gone. And this exposes one important thing about the proof. There is a subtle correction I want to make to my previous explanation. I made it sound like we could simply pick a vertex, choose the larger neighborhood, pick another vertex, and repeat. That's not by itself a complete proof of the theorem. The rigorous proof uses induction, and that actually makes your question much easier to understand. Don't show me induction. Don't show me induction. Don't think I'm picking up vertices one by one and trying to make them all connected. Think I pick a vertex, split the remaining graph into smaller graphs, and recurse on the larger one. But as you say, I chose between this and this. Do I even have a choice? Because you are saying me to choose the larger group. And if I have to choose the larger group, then I will always choose this right branch. I will never choose this left branch. Do I even have a choice here? As you say, if our rule is always choose the larger group, then there is no choice here. We must choose because it is four vertices. At each new vertex, look at the two groups again and choose whichever is larger. The two groups change completely at every step. Pick A, you get this group. Now we are inside this group. Pick F. Currently, we do not look at all eight vertices anymore. We only look at the current candidate set. Now ask which are connected to F and which are not. Find nothing. No choice. We take this, but here is where the choice actually exists. Imagine instead when we picked F, we got that isn't as option. The side you choose can change it every iteration. Now something even more important. There are actually two different ideas getting mixed together here. The pigeonhole argument at every step, sum of connected and sum of not connected should be equal to S. Therefore, this guarantees that some larger subset exists. Why am I not getting the point? Should I watch a video? What do we have when we search about Ramsey's theorem? Let's see what we have here. Red, am I connected? Okay. Ramsey's theory, I think this is the one. This is animated video. It's the desktop audio. Why is the device audio not being captured?
Organizing one can oftentimes be hellish. Who should you invite? What if you can't invite a lot of people? Will your guests mingle with each other? What's the right blend between friends and strangers? And God forbid you plan a party straight out of the silent film era. Well, according to mathematicians, there can be a way to throw the best party ever. And yes, as it turns out, mathematicians are capable of partying. So here's the problem. I want at least X people to be friends, or at least Y people to be strangers at my party. What is the minimum number of guests that I should invite? Well, we'll start with a simple case. Let's ask ourselves, how many people must be invited to a party so that we can guarantee that there's a group of 3 people who are either all friends or all strangers? Let's also assume we want to invite the minimum number of people to this party because we would like to spend as little money as possible. The answer is 6 people. Why might you ask? It's better if we show you. Let's consider 6 people, say Alice, Bob, Claire, Dan, Ella and Frank. There are 15 lines between the 6 people representing each of their relationships, whether they're friends or strangers. There are 32,768 different possible combinations. We are claiming that there is always either at least a trio of friends or a trio of strangers. Let's have a look at all the different combinations of relationships that Alice can have with the other partygoers. There is 0 friends and 5 strangers, 1 friend, 4 strangers, 2 friends, 3 strangers, 3 friends, 2 strangers, 4 friends, 1 stranger, and 5 friends, 0 strangers. So no matter the situation, Alice must be either friends or strangers with at least 3 other people. Let's say she's friends with Bob, Claire and Dan. If any of Bob and Claire, or Bob and Dan, or Claire and Dan are friends, then we will have a trio of 3 friends and the problem is solved. So we will assume that none of Bob, Claire and Dan are friends, but then we have a trio of 3 strangers. A similar situation applies for the other way around if Alice doesn't know Bob, Claire or Dan. So 6 people is enough to solve our problem, but can we save even more money while still throwing the best party ever by inviting fewer people? The short answer is no, and let's see why. If only 5 people come, then we can't guarantee anything. This so-called party problem, formerly known as the maximum clique problem, is thought.
Welcome. Today I will be giving an introduction to Ramsey theory. Consider the following question. What is the smallest number of people needed in a room in order to guarantee that either 3 people know each other or 3 people do not know each other? Eventually, I will encourage you to pause the video and think about this problem on your own. But first, I want to make
What's up, guys? Welcome to my extreme graph theory. So this in this app, or basically you 6 people. Okay, right. Any 6 points. If you color any 2 points using red, let's say I color these 2 points using red. If I using red, it means that they know each other. So this is know each other. And let's say I using blue, means that they don't know each other. Okay. Oh, okay. So I using blue. Oh, this is not blue. Oh, I should use something. If I use blue, basically means that they don't know each other. So they don't know each other. Okay. So this theorem basically say that this is red, okay, or blue. Okay. Okay, and you can play around with it. You can let me just I will give the proof, but let me just play around with it. Let me just prove it using this graph. Okay.
Where you are
So without also
already taking
generosity, I
six
can.
people. He's already taking 6 people. I want a generic proof of. Is he doing generic
Hello
proof?
and welcome to week 9, lecture 2 of CO 442642 graph theory. And way that difference. Again, this is a bit of a want to have just part that we're looking for. And it turns out
Yeah, I think he's doing the one I want. Does every large enough graph contain a large clique or independent set? This question and branch of graph theory
this
called
question and
Ramsey
related
theory.
questions are a form branch of graph theory with its own distinctive flavor. That's called Ramsey theory, after Ramsey and Ramsey's theorem, which we'll be discussing today, which answers this question. So it has a slightly different flavor than extremal graph theory, where maybe we're interested in maximizing or minimizing subject to constraints. Here, we're given something and we want to find order among it. We want to find certain substructures, assuming you're large enough. And they go somewhat hand in hand and are clearly somewhat related, but maybe distinctive enough to have been named its own subfield. So Ramsey proved in 1930 that for every positive integer r, there exists a number n, such that every graph G with at least n vertices contains either a kr, that's a clique, or a kr complement, which is an independent set, but as an induced subgraph. And so induced there just to make sure that you can't cheat with the independent set. So you can really find a large clique
At
or a
least-
large independent set. So that's what
Well, if you remember this point here, right? This is the representation of clique graph. Okay.
we'll be trying to prove
Maybe.
today. We'll be giving various proofs of that. I'll just say, though, this goes to a more general theory that therefore Ramsey started, called Ramsey numbers. Just as we have Tarot numbers, we have Ramsey numbers. So the Ramsey number of a graph H, denoted R of H, is the minimum integer n, such that every two coloring of the edges of Kn contains a monochromatic copy of H. So this is a different way to think about the problem. Instead of finding a clique or an anti-clique, you could kind of find H or an anti-H. So maybe it's better to think not of graphs at all, but of two colorings of the edges. You want to find, say, a red H or a blue H. And Ramsey's theorem is thus equivalent to the statement that R of kr exists for all R, that the Ramsey number of cliques exist. That they're actually kind of, it is well defined. There is some, number, right? All right, so that's the Ramsey number for n and h. And then why is this? So, so we have this Ramsey number that for h, there is an n that exists, but why? Maybe pause a moment and think. Why, are these equivalent? Maybe it's very clear to you, just again processing. Because Ramsey on edge clique, right? This implies, Ramsey theorem implies the existence for monochromatic cliques and therefore monochromatic any subgraphs. So there always exists this number which you can force. So that's structure from chaos, order from disorder. But eventually, if we're large enough, we can find a monochromatic copy of any H. So we're going to prove this today. So I'll give you, there are a couple of different proofs, but they're all somewhat similar. So I'll do one, which is quite nice, and then we'll talk about generalizations and prove those, which are, kind of in a sense give a different proof. But really, you'll see the way I'll do it will be the same. Okay, so proof of Ramsey's theorem. Well, for r equals 1 is trivial, right? I mean, there's no edges to worry about. Right? Finding a k1 or a k1, you're going to find a vertex, that's fine. So we can assume r is at least 2. And now what do we do? Here's the key. We'll let n be 2 to the 2r minus 3. So some exponential in r, and it turns out, as we'll talk next week when we talk through bounds on Ramsey numbers, that exponential is needed here. And this is pretty close to the best upper bounds, so we'll discuss that later. But let n be 2 to the 2r minus 3. And then here's our nice claim. So claim that for every I in 2r minus 2, there exists a vi, subset of the v of g, and a little vi in big Vi. So you can find a vertex in this set with the following.
Well, how did you take? I think I'm totally deviating from. Yeah. For the topic, I can just prove this theorem using induction. And the way it says, me make space for two piles of nodes A and B, then starting with the entire graph repeatedly, add each remaining node x to A. If the degree is greater than one half the number of remaining nodes, and B otherwise, and discard all nodes to which x is or is not connected if it was added to A or B. Continue until no nodes are left. At most, half of the nodes are discarded at each of these steps. So at least log in 2 steps will occur before the process terminates. Now each step adds a node to one of the piles. So one of the piles ends up with at least this much nodes. Add a node to one of the piles. So one of the piles ends up with at least this much nodes. The A contains the nodes of a clique and B pile contains nodes of anti-clique. Will clique and anti-clique added together be always equal to complete graph? No, no, right. If I take means that depends at if that depends on the subgraph. If I'm talking about a particular graph, let's call it a set of 8 vertices, just like here, then everyone connected to it, everyone not connected to it, basically complete picture is there, right? But if we are seeing a subgraph, then in that subgraph again the complete picture is present for that subgraph. So clique and anti-clique are always equal to complete graph. And this stream is just so it is getting difficult for me to comprehend, and I'm more than I'm almost at 1.5 hours still at this topic, but that's fine because why not? I do have a crux of the idea, but I don't understand the complete picture. I don't have the intuition of this picture. What's the intuition of this picture? Total number of steps. Guys, if I have uh, again, it is trying to annoying me. Here, the number of steps you see, in just 2 steps, I'm over. Okay, total number of nodes you see, I have 8. So logarithm 3, right? Do half. So at least 1.5 steps. But does it? Now I see exactly what Ocean is making for. You are not okay. Guys, you know what? I've actually kind of, you can say, bunked from college. I'm on a bunk and I'm studying Ramsey's theorem. I think I need to return to college. It will take me 1.5 hours. And here I'm studying. I think I won't go until I complete this. Is not generally true. This is the first thing to fix. Suppose you have this set of vertices. You pick A and you get this set. Okay. But these two sets do partition all the vertices except A. And this is very obvious, of course. This is intuitive. That's true, but this doesn't mean N of A is a clique, or this is independent. Why? Why is this not a clique? They're just two groups based on the relationship with A. For example, inside N of A, you could have K be not connected to D, which is true, which is absolutely true, which is true. Yes, B is not connected to D. Okay, so this is where. Okay. I was actually thinking if I have taken everything connected to A, it makes a click. But no, in a click, every vertex should be connected to other vertex. So is B connected to everyone? No, B is not connected to D. And similarly, D is not connected. Of course, obviously, just don't sit around, bro. Um, this doesn't mean N of A is clique, okay? Or not on a phase independent set. They're just two groups. So you were thinking clique plus anti-clique equals to total graph, but the irony is this isn't even a clique. So what are we trying to conclude? Every graph with n vertices has either a clique of this size or anti-clique or independent set. Independent set means anti-clique, right? Independent set of size. We are not trying to split the entire graph into here's a clique, here's an anti-clique, and together they make the graph. No, we are trying to find one sufficiently large homogeneous group. Homogeneous here means clique. Every pair has edge or independent set. No pair has an edge. Now look at your example. You have taken n equals to 8. And but here's something subtle. A set of vertices has integer size. You can't have a clique of size 1.5. So should be greater than or equals to 2. Therefore, for your graph, the theorem says there must be either a clique of at least two vertices or an independent set of at least two vertices. And yes, you found one. You selected A and F, and from your graph, A not equals to F. I mean, no, A not connected to F, not similar to, not connected to F. Therefore, this set is an independent set, and its size is 2. Of course, 2 is greater than 1.5, and therefore graph satisfies the theorem. So yes, for the particular graph, you have successfully demonstrated the theorem's conclusion, and your statement is true, is correct. But here's the big thing you're missing. Okay, so why all this complicated process for 8 vertices? I found A and F done. Exactly. For n equals to 8, the theorem is incredibly weak. It only promises this, and every graph with at least two vertices trivially has either a clique of size 2 or an independent set of size 2. This gives a clique of size 2. And this gives an okay. So for n equals to 8, this particular bound isn't very impressive. The theorem becomes interesting for huge graphs. This is where the intuition shift. Okay. Suppose you have 1024 vertices. And so log is of course equals to 10. 2 to power 10 equals to 1024. And the theorem guarantees that in every graph with 1024 vertices, it contains either a clique of size 5 or an independent set of size 5. Now that is interesting. Imagine I give you 1024 vertices and allow you to draw edges however you want. You might construct a graph that avoids large cliques. Fine. Then Ramsey says, okay, if you avoid the cliques, you are going to be forced into a large independent set. Then you might try to avoid large independent sets. Ramsey says, fine, then you are going to be forced to make a large clique. You cannot escape both. And that's the actual, you know what, I'm getting The what was that? What was that theorem? Uh, do I remember right? Heisenberg uncertainty principle. You cannot simultaneously know the exact position and momentum of a particle. And this Ramsey theorem of graph just sounds this uh, my war memories. Okay, think of it as a game. Imagine you are designing the graph. You have complete freedom. For every pair of vertices, you choose edge or no edge. You want to defeat Ramsey. Your goal is I will construct a graph with neither a large clique or nor a large independent set. So Ramsey says you basically can't. There are n minus 1 vertices distributed between two groups. Therefore, one group must contain at least n minus 1 by 2. Yeah, you were talking about at least, right? So, yes, that is intuitive. This is not a clique or independent set. It is merely a large pool of vertices that all have same relationship with it. That's cleverness. So, why is that useful? Suppose this neighboring group is a very large group. Okay, number of vertices in this group is going to be equal to or greater than half of all the, of course, remaining vertices. Now imagine we somehow find a clique inside NFA. Because of B, C, and D are in NFA, we already know this is going to be a clique. Therefore, this is a larger clique. That's why NFA is useful. And the independent case works symmetrically. Large neighborhood will extend the clique and large non-neighborhood will extend the independent set. That's the core mechanism. Now the logarithm finally makes sense. This is the beautiful part. You can keep at least half, you can keep at least half again, half again, half again. And after k steps, you're left with this number. K is number of steps. So number of steps is going to be less than equal to this. The number of times we can keep doing this is logarithmic. I think I get the idea now. When it told me that basically this thing right here is not a clique, kind of I felt it. Why was I even thinking this is a clique? Wait, I'm so dumb. Okay, that's interesting. And okay, I do have an intuition for Ramsey theorem of graphs, but I don't have intuition for that particular question. That question of if you want three people in a party, such that at least three of them know each other, or at least three of them don't know each other. Okay, that is the same problem. Let's say you have six. Uh, yeah, it's like connecting. If there is a connection between two nodes, then those two people know each other, of course. and in other case they don't know each other. Let's take an example with 6 nodes. I will construct just some random. Okay, this is a graph. Now I can just see these three people don't know each other. So the theorem is valid. These three people as well don't know each other. Is there any clique here? Yes. Well, this is a clique. I can find clique of 2 elements, but clique of 3 elements. Triangle. Is there any triangle? No, 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 no. So at least three people don't know each other is valid in this situation. And in this case, they do not know. Okay. How will we backtrack our steps? Let's say asking this question in reverse. I proved if I have 6 nodes, then 3 nodes are not connected to each in every possible connection. Maybe at least 3 nodes will be connected to each other such that they form a triangle. Means all these three people know each other, or I will eventually find 3 nodes. Let me connect everything. Let me make it a complete clique. If I make it completely like, then of course three people know each other. I have a triangle. So again, that is valid. So that will always be valid or invalid. Okay. I think I have just completed this chapter 0 finally. And for this 15th question, actually, I completed 15th question off stream, and I really don't want to give any more time to this chapter 0 now because I'm very excited to study regular languages. Yeah, regular languages finally. In this day 4 PDF, let's just tata, bye bye. Zernal, new document. I'll just make the background plain, and paper color is, sorry, paper color is similar to my PDFs. Oh, finally, this feels nice. The theory of computation begins with a question: what is a computer? Ah, it is perhaps a silly question, as everyone knows that this thing I type on is a computer, but these real computers are quite complicated. Okay, too much. So to allow us to set up a manageable mathematical theory of them directly, instead we use an idealized computer called a computational model. As we as with any model in science, a computational model may be accurate in some ways, but perhaps not in others. As with any model in science, a computational model may be accurate in some ways, but perhaps not in others. Thus, we will use several different computational models depending on the features we want to focus on. We begin with the simplest model called the finite state machine or finite automata. Yeah, hell yeah. Finite automata are good models for computers with an extremely limited amount of memory. What can a computer do with such a small memory? Many useful things. In fact, we interact with such computers all the time, as they lie at the heart of various electro mechanical devices. The controller of the automatic door is one example of such device, often found at supermarket entrances and exits. Automatic doors swing open when controller senses that a person is approaching. An automatic door has a pad in front of to detect the presence of a person about to walk through the doorway. Another pad is located at the rear of doorway so that controller can hold the door open long enough for the person to pass all the way through, and also so that the door does not strike someone standing behind as it opens. This configuration is shown in the following figure. Top view of automatic door. The controller is either of two states, open or closed, representing the corresponding condition of the door. So those are two states of the door. It can be either open or closed, representing the corresponding condition of the door. As shown in following figures, there are four possible input relations. Front, meaning meaning the door. Except, one second. Um, where was I? I got distracted. Sorry. As shown in following figure, there are four possible conditions. Front, meaning that a person is standing in on the pad in front of the doorway. Rear, meaning the person is standing on the pad in to the rear of the doorway. Both means the people are standing on both pads, and neither means no one is standing anywhere. So for each particular case, a state will be present. I mean, if both sides people are standing on the pads, the gate will be closed for sure. If one side, let me construct a table for it by myself before seeing. Okay, so the four states are front closed, sorry, front pad, rear pad. Okay, I can construct this table like thing like this. I'll just say front, rear, front, rear, and this is the case of only front. Okay, front, front, only front, only front. The gate will open. Okay, so the state is open, front and rear both. The gate is closed, rear and front both. The gate is closed, and the gate is open. Okay, closed, open, self case. I don't understand this diagram a lot now. Let's see, the book will explain me for sure. Neither. Okay, this diagram is also correct. I think I'm right. Anyway, state transition table for automatic door controller. The controller moves from state to state depending on the input it receives. When in the closed state and receiving input in either or rear, it remains in the closed state. In addition, if the input both is received, it stays closed because opening the door risks knocking someone on the rear pad. But if, well, yeah, the controller might start in the state closed and receives the series of input signals front, rear, neither, front, both, neither, rear, and neither. Then it would go through a series of closed, open, open, closed, open, open. Okay. Thinking of automatic door controller as finite automata is useful because that suggests standard ways of representation as in figures 1.2 and 1.3. Well, I do understand 1.3, but I don't understand 1.2 for now. Let's see. Think, okay, finite automata and their probabilistic counterpart Markov chains are useful tools when we are attempting to recognize patterns in data for sure. These devices are used in speech processing and in optical character recognition. Markov chains have even been used to model and predict price changes in financial markets. We will now take a closer look at finite automata from a mathematical perspective. We will develop a precise definition of finite automata, terminology for describing and manipulating finite automata, the theoretical results that describe their power and limitations, because besides giving you a clear understanding of what finite automata are and what they can or cannot do. This theoretical development will allow you to practice. Okay, in beginning, to describe the mathematical theory of finite automata, we do so in the abstract without reference to any particular application. The following figure depicts a finite automata called M1. Okay, the finite automata called M1 has three states. Figure 1.4 is called state diagram of M1. It has three states: Q1, Q2, and Q3. The start state is this one. Okay, Q1 is start. Q1 is indicated by the arrow pointing at it mm, from nowhere. Okay, from nowhere. The accept state Q2 is the one with the double circle. The final state or the accept state. Okay. The arrows going from one state to another state are called transitions for sure. Okay. When this automata receives an input such as 1, 1, 0, 1, you see 1, 1, 0, 1. So we do arrive at final position. So this particular string 1, 1, 0, 1 is acceptable. It processes that string and produces an output. The output is either accept or reject. We will consider only this yes no type of output because for now, because to keep things simple. The processing begins in M1 start state. The automata receives the symbols from the input string one by one from left to right. After reading its symbol, M1 moves one state to another along the transition. Yeah, can you can you describe the language consisting of strings that M1 accepts? Okay. Formal definition of a finite automata. In the preceding section, we used we used state diagrams to introduce finite automata. Now we define finite automata formally. Although state diagrams are easier to grasp intuitively, we need the formal definition too for two specific reasons. First, a formal definition is precise. I do understand why do you need a formal definition. It resolves okay, fine, uncertain about whether finite automata were allowed to have zero accept states or whether they must have exactly one transition exiting every state for each possible input symbol. You could consult the formal definition and verify that the answer is yes in both cases. See, no, both cases. Second, a formal definition provides notation. Good notation helps you think and express your thoughts clearly. The language of a formal definition is somewhat arcane. Okay, having some similarity to the language of a legal document, both need to be precise, and every detail must be spelled out. A finite automata has several parts. It has a set of states and rules for going from one state to another, depending on the input symbol. It has input alphabet that indicates the allowed input symbols. It has a start state and a set of accept states. In mathematical language, a list of five elements is often called a five tuple. Hence, we define a finite automata to be a five tuple consisting of five parts. We use something called a transition function, frequently denoted by this symbol delta, to define the rules for moving. If the finite automata has an arrow from a state x to a state y, labeled with the input symbol 1, that means that if the automata is in state x, when it reads a 1, then it moves to state y. Yeah, we can indicate the same thing with the transition function by saying delta of x1 equals to y. This transition function when takes okay means delta function basically takes two inputs such that delta, which is the transition function, takes inputs of state and one generic input from the language, and it outputs a state, a new state. Finite automata is a five tuple where Q is the set of all states. Q is a finite set of the states, okay? Finite set of alphabet. If I remember correctly, alphabet is a set of symbols. And delta function is a set. You take an element, you take any element from set of states, you take any symbol, and symbol is basically the input, okay? So formally, I will actually call them, instead of saying input, I should say, I should say symbol. Take a state, take a symbol, produce a new state. That means delta is take a state, take this and output Q. Okay. Formal definition precisely describes what we mean by finite automata. For example, returning to earlier question of whether zero except states is allowable, you can see that setting f to be empty, empty set yields nothing. Empty set, okay, yields zero except states, which is allowable. Furthermore, the transition function delta specifies exactly one next state for each possible combination of a state and input symbol. That answers our other question affirmatively, showing that exactly one transition function arrow exists every state for each possible input symbol. We can use the notation of formal definition to describe individual finite automata by specifying each of the five parts listed in definition 1.5 for sure. For example, let's return to finite automata M1 we discussed earlier. Redrawn here for convenience, fine. The finite automata M1 delta is describes as this delta function, just like I chose to draw this table, but instead of taking output on both axes, you take input, you take symbols on one axis, you take state on another axis, and then output is represented inside. Yeah, Q1 is the start state, F is Q2. Because final states can be more than one. Okay, we can actually define more than one final sets, and that's why this F is a set of final states. Yeah, and you can only start from one start state. So this is not a set. This is a literal element that belongs to set of states. If A is a set of strings that machine, set of all strings that machine M accepts, we say that A is the language of machine M. Okay, this is very beautiful thing you said. We are talking about all the five tuples. First tuple is set of all states. Set of all states, I have Q1, I have Q2, and I have Q3. Secondly, set of all symbols. Well, I have just two symbols, 0 and 1. So the language is going to be binary, right? Delta is defined as a 2D axis which contains states on one axis and symbols on another axis. I can Q1 takes 0 to give Q1, Q1 takes 1 to give Q2, Q2 takes 0 to give Q2, takes 1. Oh, I wrote something wrong, something very wrong, ambiguity, fine. Takes 0 to produce Q3. Takes 1 to produce Q2 itself, and then Q3 takes 0 or 1 either to produce Q2. So this is the transition function. Then then fourth in the five tuple, the fourth element is basically start element, which is Q1 in this case, which belongs to set of states, of course. And this set F, right, which is basically Q1 right here. No, not Q1, it's Q2 because Q2 is final state. Yeah. And we talk about one more important thing, basically a simple definition. Definition is if a machine may accept several strings, but it always recognizes only one language. If the machine accepts no strings, it still recognizes one language, namely the empty language. In our example, how much formal definition of computation? There are a lot of things in this chapter that I already know. I'm just trying to find section 1.2. Those are figures actually. There's nowhere. It's nowhere. Fine. Oh, non-determinism. Okay. So there's not much. Examples of finite automata. Fine. State diagram of two-state machine automata. Two-state. Two-state machine, okay. Consider the finite automata. This state diagram similar to M2, except for the location of accept state. Here accept state is Q1 and there accept state is Q2. As usual, the machine accepts all strings that leave it in an accept state when it is finished reading. Note that because the start state is also an accept state, M3 accepts the empty string epsilon. As soon as a machine begins reading the empty string, it is at the end. So if the start state is an accept state, epsilon is accepted. In addition to the empty string, this machine accepts any string ending with a zero. Yeah, because you will always have a zero at end to actually return to Q1. The following figure shows a five-state machine. M4. Machine M4 has two accept states, Q1 and R1, and operates over the alphabet A and B. Some experimentation shows that it accepts string A, AB, AA, BB, and BAB, A, B, A, A, B, A, B. Yes, but not strings A, B, B, A, B, 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 A. This machine begins in state S, and after it reads the first symbol in the input, it either goes either left into the Q states or right into the R states. In both cases, it can never return to the start state. In contrast to the previous example, it has no way to get from any other state back to S. If the first symbol in the input string is A, then it goes left and accepts when the string ends with A. Similarly, if the first symbol is B, the machine goes right and accepts when the string ends in B. If M4 accepts all strings that start and end with A, uh, start with start and end with A, or start and end with B. In other words, M4 accepts strings that start and end with the same symbol. Okay. There are one, two, three, four set alphabet. Okay, of shows a three-state machine M5 which has a four symbol input alphabet. One, two, three, and four. Yes. I don't know why they have written. Okay, I want to know this symbol meaning. We can continue from this example in next session because I'm already getting late for my college. Too late. Half day is finished. Okay, so see ya guys. I will continue from this exact step. I will know, try to understand what this symbol means, this brackets, angular brackets symbol, and whatever. We treat reset as a single symbol. I know we're a single symbol, but yeah, it's easy, very easy. Okay, bye.